Okay, these are the notes for section 4.2, derivatives of logarithmic functions. So these are how to find the derivative of y equals natural log x, and then more generally, how do you find the derivative of y equals log some base b that's not the natural log of x. For the proof of this, I'm going to refer you to the Khan Academy video. If you go to khanacademy.org, Khan, all one word, khanacademy.org. If you've never been to that site before, there are lots of videos, there are thousands of videos, but they're organized by topic. If you go to the calculus, just scroll down until you find all the calculus videos, and then look, they're in order of the things that you would do in a calculus class, so you'll see some things that we've done already, like power rule, chain rule, and so on. And then if you keep scrolling down, you'll see something about like proof of the derivative of natural log x is equal to 1 over x, something like that. And, well, there it is. That's the result. It turns out that if y is equal to the natural log of x, then the derivative of the natural log function is 1 over x. The slope of the natural log function is 1 over the x value. And you can find the proof there. I will remind you, just before, in case you are going to go and watch that, you need to remember something that that Mr. Khan, Sal Khan, takes for granted, which is sometime in pre-calculus, you were supposed to learn that the limit as n approaches infinity of the expression 1 plus 1 over n to the n is equal to e. This was the interest compounding more and more times. This is the formula that you used. If you wanted to compound interest, let's say n number of times, you'd use the number n here. And compounding continuously is what happens when you let n go to infinity. And that's how you ended up with the e in that formula. This also showed up as a bonus on a quiz. I think it was one of the, maybe it was in chapter 2 or one of the pre-calculus review quizzes. This showed up, and some of you talked to me about that. But you're supposed to know this from pre-calculus, that this limit is equal to e, and proving this involves knowing that limit. So anyway, you can go look at that limit if you're interested. Well, now that we know this, that y is equal to the natural log x, then its derivative would be 1 over x. Let's try doing some derivatives. So let me remind you, before we do that, of some of your logarithm rules. Your logarithm rules. There are really 4 of them that come into play here in various ways. First one, you know that if you have the logarithm base b of a times, let's see, c, say, that you can break that up. That's the same as log base b of a plus the log base b of c. Right, so if you have a logarithm of a product, you can split it up into additions. Right? I think probably in Algebra 2, maybe pre-calculus, we're more used to going this way. Right? When you have a sum, you can consolidate those as a product like this. But now we're going to use it more in some problems going this direction. We'll take a product and we'll break it up like this. Likewise, if you had a logarithm of a quotient like that, you can split that up by subtraction. If you don't remember why these things are true, you could try to prove them yourself. It's not that hard. It's just a little bit of algebra and using the definition of a logarithm. It's a good exercise. If you're interested in that, if you try and you can't manage to do it, then come talk to me about that. if you have log base b of a to some power p, then that power right there, we're going to use this rule a lot, that power right there can come to the front. Again, you should maybe try to prove that to yourself, why that works. And last, the change of base rule. This one's really important for us because we only know the derivative of the natural log function. We don't know any other base. So since we know, let's see, I'm going to do it like this. Since we're really only interested in changing things to the natural log base, instead of doing the general change of base rule, I'm going to do a rule specifically for changing to natural log. So if you have natural log log base b of a, you can change that to the natural log of a over the natural log of b. It's pretty intuitive where, the top number goes up, the bottom number goes down. These two things are equal to each other. Of course, you can change it to any base that you want, but this is the one that we're interested in because that's the one that we know how to take the derivative of. There are your logarithm rules. So for the very first extension now of this, let's say, call this example 1. Let's say we have y is equal to log base 10 of x. And we want to find the derivative. Well, we don't know what the derivative of this is, so first we change this to, we use the change of base rule, and we say, well, that means y would also be equal to, that would be natural log x over natural log 10. And remember, that's just a number, right? That's like when we see things like x over 2, maybe better for us to write the constant out at the front. So this is the same as 1 over natural log 10 times the natural log of x, right? That's better for us because now we just have a number times the function whose derivative we know. So then we say, okay, the derivative of this, that's just a number, so it's 1 over the natural log of 10 times, and then the derivative of natural log x, that's the one that we know, it's 1 over x. That's what it looks like. That's what happens when you have a different base. Okay, that's how we deal with that. Now, how do we deal with, let's say, a chain rule situation? So what if we have y is equal to the natural log of x squared plus 1? So the derivative of natural log of whatever, using the chain rule, right? Derivative of natural log whatever is 1 over whatever times the derivative of what's inside. And usually we'll write that like 2x over x squared plus 1. So the derivative of natural log x squared plus 1, it's 1 over that times the derivative of what's inside, right? That's from the chain rule. Okay, so far so good. Ooh, what's that? Maybe I need some more paper. This is all used. Let's use the back. Okay, so sorry, I hope you can't see too much of that. What's bleeding through from the other side. And you see that up there? Yes. So example 3. Let's do another chain rule, but a little bit maybe weirder chain rule. How about the natural log of sine x? Some of these might be might end up being homework problems, but that's not a problem. And we want to find the derivative. So the derivative of this, the derivative of natural log of whatever, is 1 over whatever times the derivative of what's inside. The derivative of the sine function is cosine function. And, well, that's interesting. I mean, 1 over sine x times cosine x, if we wrote that as cosine x over sine x, that is the cotangent function. And isn't that interesting? The derivative of the natural log of the sine function is just the cotangent function with no natural log. This is another hint, maybe, that there's some very deep relationship between the trig functions and the radians that they operate on, like pi, pi over 2, all that stuff, and the number e. Right? Somehow, taking the natural log of a sine function, when we took the derivative of that, we got only a trig function. So there must be some kind of relationship between that if the e, the base of this, just completely disappeared when we took the derivative. You remember what our first hint was? Would you pause for a second and think about what was the first hint that there was some relationship between those? I'll let you think about that. Let's see. Example 4. I'll just do one more example like this. Well, let's make it a little harder. Let's involve both of these things. So, what if you had log base 2 of the, let's see, how about of x squared over x plus 1? Now we got a couple things to deal with here. This is not the right base, so the first thing we have to do is our change of base rule. That would be the natural log of x squared over x plus 1 over natural log 2, right? That goes up, that goes down. And probably better for us to write that that's just a number times natural log x squared over x plus 1. Okay? And that's as far as we want to go with our y. And then the derivative would be, that's just a number, that's a constant, whatever 1 over natural log 2 is, times, and then the derivative of natural log whatever is 1 over whatever times the derivative of what's inside, and then the derivative of what's inside, we'll have to use the quotient rule. So that's low d high minus high d low all over low low. So how much simplifying do you want to do? Well, I think we need to do a little bit. We can't leave that like that. And of course, 1 over something just flips it over. So looks like we have 1 over natural log 2 times x plus 1 over x squared times a little simplifying on the top. X times 2x is 2x squared minus x squared is x squared plus 2x over x plus 1 squared. Okay, and then we could look for a little bit more simplifying to do if we wanted to, and I will in this one go all the way. So I've got an x plus 1 here, and I've got x plus 1 squared here. So that could cancel with one of those. And then here, x squared plus 2x, there's an x that could be factored off of that. So that's x times x plus 2. I'll write it in its factored form. And then notice I have an x here and 2x's here. So this x could cancel that extra one. So what do we have left? We've got 1 over natural log 2. And then I've got an x on the bottom and an x plus 1 and an x plus 2 on the top. So it turned out the derivative of log base 2 of x squared over x plus 1 is 1 over natural log of 2 times this rational expression here. If it had just been natural log to start with, how would that answer be different? Think about that for a second. And pause. Well, it would be different. That wouldn't be there, right? You wouldn't have had to do the change of base. We would have just started with this, right? So the only difference is that shows up if it's the wrong base. The wrong base means anything besides e. Oops. Okay. You can do, see what we're doing. We're at 15 minutes, so I think you can find some more examples in the book. Try a few of the odd-numbered problems if you would like to get ahead of the game. And I'm going to do another example for you. I think we're on example 6 now. Is that right? Nope, example 5. I'm going to show you something called logarithmic differentiation. This is where our logarithm rules really come into play. Logarithmic differentiation. Alright, what does this mean? Let's say we have some really horrific looking function like this. Y equals x plus 1 to the 7th times x minus 3 to the 8th over x squared plus 2x plus 5 to the 3rd. Now we could take the derivative of this. We already know how to do this. It would be quotient rule, and inside the quotient rule there would be a product rule and then chain rule for each one of the individual things. So it would be a big mess, but we could do it. Well, there's another way to approach this. We could try, right at the beginning, instead of working with this, try taking the natural log of both sides. You know, since the early days of pre-algebra, you can do whatever you want to an equation so long as you do it to both sides. Sorry, that's a 1. Started to write a 7 there. You can do anything you want to an equation so long as you do it to both sides. Okay? Now, why would we want to do that? What's the advantage of doing that? Well, using logarithm rules, you know that a product turns into addition and quotient turns into subtraction. So breaking this up using logarithm rules, that's the same as the natural log of x plus 1 to the 7th plus the natural log of x minus 3 to the 8th minus, because this is on the bottom, the natural log of x squared plus 2x plus 5 to the 3rd. And then by another logarithm rule, these exponents can come out to the front, right? So the natural log of y is equal to 7. I'm just going to bring each one of those out to the front. 7 times the natural log of x plus 1 plus 8 times the natural log of x minus 3 minus 3 times the natural log of x squared plus 2x plus 5. And now I'm going to take the derivative. So, what's the derivative of natural log y? Well, we know from the last section, anytime you take the derivative of something with a y in it, a dy dx pops up. So, the derivative of natural log y is 1 over y times dy dx. What's the derivative of 7 times the natural log of x plus 1? It would be 7, that constant, times 1 over x plus 1, right? Derivative of natural log of anything is 1 over that thing. It may be chain rule times the derivative of what's inside, but the derivative of what's inside is just 1. Plus 8 times derivative of natural log x plus 3 is 1 over x minus 3. Derivative of what's inside is just 1. Minus 3 times the derivative of natural log of x squared plus 2x plus 5 is 1 over x squared plus 2x plus 5. I didn't write the 1 down because after you've done a few of these, you know if there's chain rule, the top thing is just going to end up here, or the derivative of what's inside will end up here on the top. So you could write a 1 there, and then we have to multiply by the derivative of what's inside, which is 2x plus 2. And we kind of have our derivative, but notice here we don't have dy dx. We want to just solve for dy dx. So I just have to multiply this over to this. I have 1 over y here. If I multiply both sides by y, that will move the y to the other side. And remember what y is? Y is the original function. So I'm going to write a big Y. So this is what? 7 over x plus 1 plus 8 over x minus 3 minus 3. You can distribute the 3 through or leave it factored out, does not matter, over x squared plus 2x plus 5. And then, depending on what you want your answer to look like, if you don't want it to have a y on this side, we know what y is equal to. So here's the whole big, ugly, messy answer. It's x plus 1 to the 7th times x minus 3 to the 8th over x squared plus 2x plus 5 to the 3rd. That's y, right? This is our original y equals. That's our y equals, right? Original function times this. 7 over x plus 1 plus 8 over x minus 3 times 2x plus 2 over x squared plus 2x plus 5. So there you go. You might be thinking to yourself, well, was that really better than using the product rule, quotient rule, chain rules here? Yeah, I think I wrote out like an all with every single step here. But with a little bit of practice, this actually, I think, goes much faster, and it's less error-prone than doing it the other way. I'm going to sneak one more quick example of that in here. So let's just do one quick one. I'd like you to pause and try this one yourself. So what if you had this, the cube root of 3x minus 1 over, let's see, x squared plus 7x to the 9th. Can you use logarithmic differentiation here? Sure. Remembering that the cube root of something is the same as that thing to the 1/3 power. So maybe right away we want to say, oh, that's the same as 3x minus 1 to the 1/3 power. So take the natural log of both sides. And then you've paused, right? You already tried it? Okay, you're back. Now, that's natural log of 3x minus 1 to the 1/3, but I know what's going to happen here. That exponent's going to come to the front, right? So the 1/3 comes out here. This is a quotient. There's only one thing on the top, so I have minus. You'll leave a little space in here. Natural log of x squared plus 7x to the 9th, but I know the 9, that exponent will come out here. And then we take the derivative. It's 1 over y dy dx equal to, the derivative of this is 1/3 times 1 over 3x minus 1 times the derivative of what's inside minus 9 times the derivative of natural log whatever is 1 over whatever times the derivative of what's inside. And then final step. So dy dx is equal to y, which is the original function. I'm going to let you sometimes just write the y, that way we know what y is equal to, and I know that you can dutifully copy it down again. But we just put a big y there because we know what it is. It's right there. And then a little simplifying. 3's cancel. 1 over 3x minus 1 minus 9, 2x plus 7 over x squared plus 7x. And that's not too bad, right? So that is logarithmic differentiation. Okay, good luck. Try some of the book problems. You probably pick some that are our homework problems anyway, and that'll get you ahead of the game.